This video is related to practicing drawing free body diagrams on forces that are acting on objects that are going through a circular path. So essentially this is part of our note packet, and I am just videoing my discussion on that. So first we have a car that is traveling over a hill, and it should have been at the top of the hill. So here's my car. And if I draw a dot that represents the car, the forces acting on the car is force normal and force of gravity pointing downward. Now you need to imagine that this curvature, this hill, is a part of a circle, and this axis of rotation, which I highly recommend putting near your free body diagram, is actually below. And so I'm going to sum the forces not in the y, but in the inward direction. And the rule is, excuse me, that forces pointing towards the center of the circle are positive. And in this case, force of gravity is pointing towards the center of the circle, which is why I have shown reference near my free body diagram the location of that axis of rotation. So there's my axis of rotation. And force of normal is outward, so that's why it's negative, and that is equal to the mass of the car times the centripetal acceleration, not the acceleration in the y. So I can write Fg minus force normal equals, and then centripetal acceleration is v squared over r, which is also r omega squared. So mass v squared over r, which is also mass times the radius times the angular speed. So there's Newton's second law applied to a car going over a hill. I can do the same thing with the car that's going in a dip. This is at bottom of the dip. And if I put a dot that represents the car, and I have force normal up, and I have force of gravity down, again, where is the axis of rotation in this circle? And here's this radius, right? This is the radius of that circle. Recommend putting that dot near your free body diagram so you can see. So I have the sum of the forces, not in the y, in the inward. This time force normal points towards the center, so it's positive. Force of gravity points out of the circle, and so it's negative. It equals the mass times centripetal acceleration. And I can then, of course, plug in v squared over r or omega squared times r, depending on what the information in the problem is. Again, v squared is the linear tangential velocity of the car. Omega is the angular speed of the car. So now we have a stopper on a string. This is a vertical circle. So here's my axis of rotation, and this is a stopper on a string, and there's at the top. If I make a, this is the radius, this is the axis of rotation. Now I have a free body diagram. I'm going to make this dot a little bigger. I have two forces acting on the stopper. I have force of gravity downward, and I have force of tension downward. Both of those forces are in the direction of the axis of rotation, which is in the center of the circle. So both of those forces are positive with our rules. Forces inward, there's two of them. There's force of gravity plus force of tension equals the mass of the stopper times centripetal acceleration. And again, I can plug in whichever I would like, depending on what the problem gives me as far as the definition of centripetal acceleration. That's the only direction I can sum the forces. I got a vertical circle with the stopper at the bottom. So here's what that might look like. This is my axis of rotation. This is the radius. And I'm going to draw a dot that represents the stopper. And I have force of gravity outward. I have force of tension inward. Where's my axis of rotation? It's above force of tension. I will sum the forces inward. Force of tension points towards the center. So therefore, force of tension is positive. Force of gravity is outward, so it's negative. Mass times the centripetal acceleration, and then I can use the definition of centripetal acceleration to use the velocity, linear velocity, or the angular velocity. Stopper on the string, vertical circle at the side. It is a vertical circle. So Earth is downward. Here is the center. This is an axis of rotation. There is a string. So you can imagine force of gravity pulling this way, force of tension pulling to the right. So here is the free body diagram, force of tension to the right, force of gravity downward. This is the location of that axis of rotation. I can now sum the forces on this multiple ways. Sum the forces in the y direction equals, I'm going to call down negative, excuse me here, and this is this direction, so that's what we're doing. We have negative force of gravity equals mass times acceleration in the y direction. Depends on if I'm accelerating or not and whether or not that's 0. Then, which I have to be actually, anyway, I could sum the forces inward. I'm going to do that. Sum the forces inward. That equals force of tension is positive because it points towards the center of the circle equals MAC. All right. Vehicle navigating a turn. So here's my car. This is the top view. So I'm just imagine it here. Actually, I'm going to draw it a little differently. Here's the turn. Here's my vehicle. Here is the axis of that rotation, and that's the radius of curvature. This is top view. This will be side view. So if I look at it through the paper, here's the road. Okay. We have force of normal upwards. We have force of gravity to the downward direction. And we have force of static friction inward. And we need to draw the axis of rotation of that curve. I can sum the forces two ways. In the y direction, it equals force normal minus force of gravity, which equals mass times acceleration in the y. This is 0 because I'm not accelerating out of the earth. So that's in the y direction. Then I can sum the forces inward. Forces inward are positive. That's static friction. That's the only forces in that plane. And that is equal to the mass of the car times centripetal acceleration. And that is in the inward direction. And there you go. Those are the two directions. Roller coaster at the top of the loop and at the bottom of the loop. So here comes the roller coaster. I hit the top and then I hit the bottom. And this is on forces acting on the person. So if you can imagine the person is sitting on a seat. Okay. So I'm going to either be at the top, A, or at the bottom, B. All right. So this person, come on. Is sitting in the roller coaster on a seat. So there is a force normal pushing on the person in this, what I have shown here, and a force of gravity in what I shown here. Now I got to think about it at point A and B. Okay. So let's do B first because it's exactly like what I just drew. At B, I have a dot. It represents the person. The roller coaster is sitting like that, and she's sitting on that bench, we have force normal acting on the person, and we have force of gravity acting on the person downward. The axis of rotation is above force normal, so I will sum the forces inward. Force normal is positive, force of gravity is negative, and it equals the mass of the person times the centripetal acceleration, which we can plug in information related to velocity or angular speed and radius, depending on what they're asking about. And then at A, this is the dot that represents the person. She's upside down. She's still got her rear end on the seat. Force normal, downward, force of gravity, downward. And now I will sum the forces inward, and it is equal to, both of them now are pointing towards the center of the circle, so they're both positive. And so this is at A, and this is at B. Now, if I have a satellite that is orbiting the Earth, I have only one force acting on the satellite, and it is the force of gravity. I'm sorry. And we have to use the big G equation, m1, m2 over r squared. R is the distance of the center of masses. So I'm going to sum the forces inward. There's only one. It is the force of gravity acting on the satellite. It is then equal to the mass of the satellite times the centripetal acceleration of the satellite. And then I will plug in mass of the planet. I don't know what I just did. Mass of the planet times the mass of the satellite divided by the distance to other center of masses squared equals mass of the satellite times centripetal acceleration. And then I will plug in whatever information I can or need to for centripetal acceleration. Okay, how about this one? This person's in a ride. I have force normal from the sidewall. She spins, she's pinned to the sidewall, the bottom drops out. She wants to slide downward, but the only thing that's stopping her is static friction. So I can sum the forces in two different directions, in the y direction and in the inward direction, because the axis of rotation is to the right. So I will sum the forces in the y direction first. Force of static friction minus force of gravity equals mass of the person times acceleration in the y, which in this case is 0, because she's stuck to the wall. She's not accelerating in the y. And then I will sum the forces inward, and that will equal force normal. That's the only force in the inward direction. And that equals the mass of that person times centripetal acceleration. So a couple things I'll point out here. Don't forget that force of static friction is less than or equal to mu s force normal. So there is a relationship between how the speed at which it's traveling and force normal, which then affects how much static friction is present. So the faster I'm spinning, v squared over r, the larger the force normal is, the larger the force normal is, the larger the force of static friction is. So there's a minimum speed. This number for force of static friction has to be high enough to overcome the force of gravity. So that speed will impact force normal, which will then impact force of static friction. One more to go. A stopper on a string that's traveling horizontally. You got to pay attention to the forces. I got a string, there's force of tension. And although it's sometimes hard to see, the axis of rotation for that stopper is actually in the middle of the air. And so we care about the forces that are pointing towards that middle of air. The force of tension's upward, the force of gravity is downward, and then I have this horizontal plane that has this theta here, and I have to break this force of tension up into components because it is no longer in an x or y or inward. That'll be force of tension that's opposite of theta, so that is sine theta. And then I have a piece that points upwards, and that's adjacent to theta, so that's force of tension times cosine theta. Now I can sum the forces in the y direction. The sum of the forces in the y direction is equal to Ft cosine theta minus force of gravity equals mass times acceleration in the y. And if that is going at a continuous speed around that circle, that acceleration in the y direction will be 0. And then I can sum the forces inward, not x, and force of tension sine theta is positive because it points towards the center of the circle, mass times centrifugal acceleration, and then that will be in this direction, which is inward. And that's how you sum forces on a conical pendulum. And that's it.